Welcome to today's webinar about Coreform Flex, a demonstration of next generation FEA solver on four challenging problems. I'm Matt Cederberg. I'm a co-founder at Coreform, and today the webinar will be presented by Greg Vernon, the Coreform Director of Engineering. And throughout the webinar, feel free to ask questions in the chat. We'll answer them back either asynchronously or Greg can answer those at appropriate breaks. And with that, I'll turn the time over to Greg.
Thanks, Matt, and thanks everyone for attending today. Just a quick overview of what we'll talk about today. Just a brief introduction to Coreform and Coreform Flex, as well as some of the important things to know about Coreform Flex. And then we'll also demonstrate then the problems, which is why you're most likely here. So a little bit about Coreform. Coreform was founded in 2014 with the purpose of radically accelerating the engineering design process through isogeometric analysis. We've developed or been developing isogeometric analysis even from before 2014 when our co-founders were investigating this really since the early 2000s. And we're located in the great state of Utah. So a little bit about Coreform Flex, and really the fundamental things to understand about Coreform Flex is that from a business perspective and from a workflow perspective, it enabled a fully automatable mesh-based workflow. What this means is that whereas in traditional simulation approaches, you spend a lot of time building meshes for your simulation. In fact, studies have shown that upwards of nearly 75%, likely even more nowadays, are spent just in processes related to meshing. But this means that now you don't need to spend that time building these meshes. That's enabled through what we call volumetric trimming of spline meshes by CAD geometry. So it's important that today we support traditional CAD BREP models such as like a step file. Coreform Flex uses a technology that we've developed at Coreform called the Flex Representation Method, or FRM. And the important thing to understand about that underlying technology of Coreform Flex is it is a generalization of the finite element method that is based upon a core technology called Bezier extraction, which itself is then a generalization of the finite element method assembly process. So if you really want to understand what Coreform Flex and isogeometric analysis are about, I recommend that you look in the open literature because there's a lot of it about Bezier extraction. And that's really what links it to the finite element method. And what this means is that anything that can be supported in traditional finite element method, such as material nonlinearities, plasticity, contact, fracture, element death, multi-physics, any of those capabilities are then compatible with the Flex representation method. Today, Coreform Flex is a new tool, and it's in its initial development stages, and not all of that functionality is maybe supported today in Coreform Flex, but any of it can be developed as our customers need it. And then some of the features that are available today inside of Coreform Flex, we have a released functionality for linear elastostatic problems. And then in our beta release for our early adopters, we have nonlinear structural mechanics, including explicit and implicit time stepping methods, large deformation, nearly compressible solids, metal plasticity, contact, and others. So that's just a sneak preview of, also we have a new graphical user interface. I'll be showing our last released version of Coreform Flex today, so it'll look a little bit different than what you see on the right. But we care a lot about the user experience. So now what I'll do is I'll jump into some of the applications or these example problems of Coreform Flex. What we'll start off with before doing live demos is an overview. So this is a capability that uses the linear static functionality. This is a topology optimized radar dish and support. So a potential application shown here on the left, where you have a dish that's then supported by some mount onto a platform. And as you can see on the right here, we have this radar dish that maybe looks like a traditional manufactured approach where it's got ribbing, and then the support has been designed via topology optimization and has had an organic spline surfaces laid over it. Problems like that tend to be challenging for traditional FEA approaches due to the organic structure. But the approach with Coreform Flex and to use volumetric trimming is that each of these individual parts can just be immersed in a spline mesh that is then trimmed to the CAD geometry where the simulation occurs on. Should also note that this is an assembly, so it has, and this is for a natural frequency extraction, so it has tie constraints that tie the support to the dish. Another application that exercises the nonlinear capabilities of Coreform Flex is this large deformation problem for a flex cable bending. The customer here wants to explore the potential for delamination between the adhesive Kapton and copper trace layers. Traditional FEA approaches would require that, so there is a cable that, or sorry, a trace that crosses the other trace on the top layer. But in order to build a body fit mesh, it requires essentially projecting that bottom trace all the way through the entire geometry, which can then start to lead to sharp angles in the mesh, as well as if you have a real cable that may have dozens of traces, the process of getting all of those layers projected through in order to build this body fit mesh can be quite challenging and can lead to poor mesh quality, in addition to the time it just even takes to do that. But with Coreform Flex, by just being able to immerse each individual component in its own spline mesh, essentially eliminates all of that pre-processing time and doesn't result in these poor quality elements. And so what that means is that now these flex cable applications can just be fully automated in their analysis workflows. So now what I'll do is I'll actually now do some live demos of the tool. First on this additively manufactured fin stock chamber. So an example application here is that we're seeing with additive manufacturing, we can now develop these heat exchangers that have these internal cavities that can be printed as a single monolithic part. And so this component here, what we'll see is that there's these internal fins that are kind of at varying different angles with each other and with fillets and pose a simulation or a difficulties with traditional meshing workflows. So I'll hop out now to a live demo of this. So this is this fin stock chamber that we have here. I've already done some of the model setup, but I'll walk through what the different components of this are. So the first question is, how do we build a mesh for this model? And the mesh is simply done by creating a mesh that then immerses this geometry. So I've chosen to use a rectilinear background grid, so a bounding box within a mesh size here. Maybe the initial mesh size is 0.1, which we can see is too coarse, but we can see these actual elements here are the red kind of squares that you see on the extent of the bounding box. If we want this to be a finer mesh, we can just type in smaller mesh sizes and then drive this 0.025. And then drive this to whatever level of accuracy we need for our model. I may even go one mesh size smaller just to try to capture this opening here. And that's the extent of meshing. So whereas traditional approaches, again, I have to be doing defeaturing, I might be doing partitioning in order to fit my mesh to the model. I don't do any of that here. I am now done meshing, and I can move on to what's um, important to me, which is setting up the actual problem itself. So the process we recommend for our early adopters in Coreform Flex for setting up their problems, let's call this AM FinStock, is to start by creating a procedure. So in this case, I've created this procedure where I just want to compute the stress on this model, and I've chosen the solid mechanics physics application here. Um, and then the recommended workflow is that within your solid mechanics procedure, or whether you're doing heat transfer or modal analysis, is that there's the flex model, which is the assembly of individual parts that might exist, and assign to each part materials, define the interval for your procedure, assign time stepping methods, your boundary conditions, load conditions. So really defining the problem. And as you work through this procedure, it'll take you to different parts of the model tree. This is something that we are improving in our latest development versions from a user experience perspective. Um, but I'll just walk through some of these individual steps here. So the first thing we've done is we've added a flex model where we've defined the part that we want to have in our assembly. So we want this fin stock and a material and its material model. Notice that in this material that I've used, I think this may not have updated, but I've used an elastic material model, which is the elastic material model is a small strain assumption um, that I have assigned to this. Um, so that's the material for this. Again, I could change this if I wanted to say like 36. But if this is aluminum, then it's going to be probably like closer to 10E6. Um, as you finish your materials and assign them to the parts, there are some additional options that there are good defaults for, but we don't necessarily recommend changing. After defining your flex model, you define your interval. Here I've got a run interval that I've assigned, which runs to a time of just 1. So this is going to be a linear static solve. I don't need to have any sub increments. I can just solve it all in one go. Next, we'll talk about like just the time steppers. Again, I mentioned this is going to be a linear problem, but for any given time steppers, we support in our beta functionality some nonlinear time steppers. So a continuation method, which is a implicit nonlinear static method, as well as implicit dynamic methods that are based on generalized alpha, and explicit dynamic methods based on central difference method. These solvers are all fully parallelizable. The linear solvers that are even used for the nonlinear approaches of the implicit dynamics and implicit statics use direct solvers that are provided by a fully parallel high performance computing library. So you can run these problems on multiple cores for improved performance. The next thing that you would do is you would assign your boundary conditions. I've already done that here, but what I'll show is that what's important to do is to assign sets. So we have a set manager. We're able to come through and assign or select surfaces or volumes, curves that are involved in a given condition. So if I wanted to say change this boundary condition from being an X symmetry to maybe I want to hold the top of this volume, I can just change my surface selections. I can also change the name. So maybe I want to hold top surface. And then I'll just, for the individual boundary conditions themselves, that surface that's in the boundary condition has automatically updated to be this hold top surface. We also have then the ability to choose, say, all these internal surfaces. We can select, I'm going to clear this set out here real quick, just so you can see this process. The ability to I can select the entire cavity, which will speed up the selection of set entities, and then I can choose to select continuous to get more. You can see there's some of these surfaces that maybe don't get selected, and so then from there we can select. There you go, got all those surfaces from that continuous selection. So that saves us, as you can see, a lot of button clicks that would otherwise have to be done manually to select all of those surfaces. So you can see here the actual simulation we ran. We'll go and we'll look at the results. But I did run with the X symmetry as opposed to the top surface. We also then created a load condition, which is just an applied pressure on the internal surfaces. And the options we had for those load conditions, we could do like surface tractions, pressures, body forces, line tractions, but we've chosen to use a surface pressure here that takes a function, in this case, a constant value, and then we just scale it by 350 so that to have a 350 psi load on those internal surfaces. Then what we've also have is we have our outputs, and we have outputs on both a probe, where we can probe along a line. So we can probe a field value along this line. So in this case, pick two locations, request 200 points, and then we want to get off the stress values of those points. We can also choose to request the maximum von Mises stress, so an extremum value in that field. So a maximum von Mises stress. And then at the location of that maximum von Mises stress, I can not only report the max von Mises, but say I wanted to report the magnitude of displacement at that location. I can query those values as well. What's important to note with both of those is that those are, again, completely independent of the mesh that I'm using. I don't have to make sure that they align to nodes or anything. I can just pick arbitrary locations to query and then change the mesh as I want. And so that's another just workflow improvement that Coreform Flex provides to users. And then we just request those probes as results. We also then have field output. We currently view our results in peer review. And that's what I'll show next, is just show these results in peer review. So this is now just looking at these results. I've done a cutaway or clip in peer review just so we can see the internal surfaces. And we can kind of see that we've got this internal pressure. So we don't have a lot of deformation where these fins are providing structural support. And so it makes sense that we have our maximum deformation kind of in this initial chamber that's got the least amount of support. And we can also plot this by, say, von Mises stress in these locations. So that's this additive fin stock example. The next example I want to go over or demonstrate, which may be of interest, is this implicit dynamic problem that involves contact and nearly incompressible elasticity. This comes from an application in direct inkwrite pad testing. So you can see here on the far left is an example of what one of these pads looks like, an approximate size of these pads. They're additively manufactured with these little silicone threads that allow for building foam materials that can be engineered as opposed to a stochastic blown foam. And then this test kind of replicates this idea of, if I take this pad and I compress it, polymeric materials tend to get compression set if they're compressed for long periods of time. And so if we compress this material to some compressed state, the testing is then looking at how do these materials age and set permanently. And just to talk about like some of the difficulties that this method has before we dive into the demo, is that traditionally, in order to build a body fit mesh, one would have to do a lot of partitioning, effectively almost building a hex mesh by hand through partitioning of the model in order to build this quality hex mesh for this problem. And this quality hex mesh is then required in order to be able to get convergence of the nonlinear solution in a reasonable amount of time while also getting accurate results. And you can already see that for this relatively small subsample of that pad, there's already thousands of subcells that have been computed or partitioned, and I think it was about 100 web cut used to produce this. Whereas what we'll see in Coreform Flex is we can just simply drop this in a box and simulate. So fully automatic workflow there. So we'll demonstrate this as well. Just for today, I'm going to show this on a smaller sample than that full model, because we'll actually be able to run this in a Python script. But what I wanted to point out is that Coreform Flex not only does it support the immersed approach, but in cases where meshing is trivial. So for these, I just color here by part, for the orange and yellow regions, there's no reason to have to immerse those in a box. Those can just be automatically body fit. And so what we'll see actually in our meshes is we actually can produce body fit meshes on those regions, as well as then an immersing mesh on the difficult to mesh regions. And that's a good compromise between performance of the solve and of model setup time. And so in the cases where we have these body fit meshes, it really is very closely directly linked to the finite element method that you're familiar with. But again, meshing is a trivial or an almost trivial process. It's just a matter of choosing a reasonable element size for the problem and then moving on with actual setup of the problem. So if we do this here, again, I created a procedure for this compression of the pad and a solid mechanics problem. For the Flex model, I've instanced the pad and the platens with a material from the literature. You can find the documentation of that material on the links from the original slide. And giving it a neo-Hookean material model that if we look at this neo-Hookean, we support being able to provide a if you look at these shear modulus, this is a Poisson ratio about 0.48, but we can even increase the the Poisson ratio to the nearly incompressible of 0.49, 0.499. And we have the ability to use pressure stabilization to be able to accurately then solve this problem efficiently. After assigning those materials to different parts of our assembly, we can then just move on with defining boundary conditions. I should say with the time stepping method, we're using an implicit dynamic method here. Again, this is a beta functionality, but as you can see, we're using it on a large number of our different problems. Again, this is a generalized alpha with a spectral radius of 0, which gives us an almost quasi-static response. Assigning a boundary condition is then simply assigning symmetry conditions to the pad and to the platens, and then defining a displacement boundary condition on the top pad. Again, those sets are defined in our set manager. I'll color by sets here so we can see those. Just choose some colors for these different sets. Just so we can see that there's those boundary conditions we have for symmetry and the displacement. One thing I want to point out, if we look at any one of these boundary conditions and just tweak, say, a value briefly, I'm going to change the displacement. Instead of being 0, I'll change this to 1. Coreform Flex is based on a principle of wanting to be able to do scripting. And so every command that you can execute through the different GUI entities are echoed commands. And for problems like this, where we want to maybe run different sizes of thread diameters and spacing, different amounts of threads, we really want to be able to do Python scripting. or automation of this model setup. And so what we've done for this problem, and I'm going to show shortly the Python scripts to automate this, are copying the commands that are issued by Coreform Flex and then putting those into Python scripts. So for instance, we have this Python script here that builds through Flex commands passing in those strings that were issued by Coreform Flex, which allows for complete automation of the model setup for different pad volume ratios and thread diameters. We'll go into this in a little bit more detail in a little bit. But that's essentially the entire workflow, is just to go through and set up all the boundary conditions. We also have contact. So we just have a base contact with friction here that defines, I think, a friction coefficient of 0.3 for a Coulomb friction model. It's just assigned to every surface in this assembly. So I haven't had to go through and choose surfaces for it. It just automatically computes all the surfaces that are in contact. And then we can also probe the reaction forces of this platen. So what I'd like to do now is just show where, if you're interested, you can actually run the Python scripts, or the Python script that runs this problem, if you're one of our early adopters, just to see how this works. We have a GitHub repository that has several examples of automation with Python. And we have this direct ink write pad example. And so what I want to just walk through a little bit is how this is structured. Again, for full automation, we can run this top level Python script that has several test cases that have been pre-set up. You can choose which test you want to run. And then all that happens is that for a given test is we can run Coreform Cubit that creates the geometry and assigns those sets, and then it runs Coreform Flex. So Coreform Cubit is our traditional meshing software that also has capability for geometry creation and modification. So the commands that run or that generate this model are then all of these Cubit commands. Cubit supports a very robust Python API that's able to then create our geometry and assign all of our side sets. And so if you're interested, I recommend reading through or investigating this Python script to see how we create this geometry. But it creates the offset layers for the threads, as well as the platens themselves and the full pad. And then building the flex commands, again, through using the flex Python API to pass in all of those commands via strings. And at the very end, we even then fit our data, the reaction force data, with some Python tools that fit that. And so the point of this overall example is to show how Coreform Flex and Coreform Cubit can be integrated within your existing Python-based automation workflows due to their Python APIs that support that. And so if you have questions, you can leave questions on the GitHub repository. Our GitHub organization is Coreform LLC, and this Flex Python examples is the repository that contains this. But then we actually ran this simplified model. I only ran it just for speed. They ran this this morning. I just ran it to about 70% of the desired compression. But we can play this just so you can see that we have the contact between these different individual threads. And again, using peer review to do the visualization of this simulation. So with this model now set up, this model took about an hour total to run on my laptop, um, and running on 2 cores for this example. Um, yeah, I think just moving back to the slide deck, those are the examples I wanted to share today. Um, and I'll open it up to questions if we have them.
Yeah, Greg, thank you very much. It's exciting each time we get to show the progress here. Okay, so there's a few questions here. From Jeff. For those 2 examples that you showed, can you roughly compare the solve time for equivalent accuracy using traditional FEA methods?
Yeah. So that is a good question to ask. We don't have any verification in this case against the initial data. But what I'll say is that um, for these problems to run in approximately an hour with an implicit method, the customer that we originally developed this for was using mass scaled explicit dynamics to get solutions, or had to do other things in order to be able to kind of reduce the validity of their model in order to get implicit solutions. So I think what you'll find with the approaches that we tend to take, we tend to be within an order of magnitude in terms of solve time to achieve a similar level of accuracy. Um, and really, again, that's because what we're doing really is just the finite element method that's just been improved upon in a few key ways to support this meshing free workflow. Um, but I don't have, for either of these examples, I don't have um, um, other results to compare against.
Okay, from Hadi, in biomedical engineering, we need to show that the results, especially stresses, are mesh independent. And so they usually in ANSYS run mesh sensitivity analysis and refine the mesh. Do we have ways of refining the mesh in Coreform?
Yeah, so today we don't support local adaptivity or local refinement in Coreform Flex. So the approach that we take today is we just run multiple simulations at different mesh densities and just observe the convergence. Um, the ability to do local refinement is a core feature of spline meshes in general. And so that's something that we want to do. Um, but it's not something that we have today in Coreform Flex. But I will say that our technical team has a lot of experience developing local refinement um, um, in splines, and our U-spline technology support local refinement. So stay tuned.
Thanks. From Mohammed, can you capture complex round features using this hex mesh method?
Yeah, we can. I have a couple. I have a couple slides that I just prepared as backup, but that maybe would be helpful to show. Um, so this kind of method that we call this volumetric trimming, just the animation on the left here, just has like this spherical recorder spherical cutout in it that just kind of demonstrates that we're able to capture in our volumetric trimming approach those complex curved surfaces. Um, really, just it's a matter of the trimming tells us how to integrate our elements over those trimmed regions or cut regions. So yes, we can absolutely support complex curved surfaces um, with our approach.
Okay. From Tyson, are the stiffness matrix and load vector available through a PET-C for Pi interface in Python?
Um, I would say Not probably not really. I mean, you could probably find a way to hack it to do that. We are developing an interoperability library um, with under some SBIR. So SBIR um, is a U.S. federal funding program for that allows small businesses to do research that are applicable to the U.S. government and its departments. And so we have been working on developing an interoperability library um, and working with the open source Moose solver from Idaho National Labs on that. Um, but I would say that that's not something that's released today or is available. Um, but if you're interested in that, we can talk more about how to enable that for you.
Yeah. Another question from Tyson. Is the trim process parallelized or is it just the linear solver that's parallelized?
Yes, the trim process is parallelized. Um, sorry, I realized my screen stopped sharing. The trim process is parallelized and the solver is parallelized. Yeah.
Okay. How much error do we see compared to traditional finite elements?
Yeah, that's a great question. One of the things I'll recommend is that we have some public facing documentation. If you go to docs.coreform.com, we have a verification manual. Um, I think I mentioned this, that when we call features released, what we really mean is that um, we call in production that we have verification problems behind them as well. So a lot of our beta functionality is simply beta because we don't have verification problems published yet. But what you can see here is that, um, for example, there's this cantilever beam with an end load, um, and being able to converge to exact analytic solutions. Say if you use a cubic basis, um, and the quadratic basis as well corresponds to what you would see with traditional FEA. So it really is, if you take traditional finite elements, you use high order smooth splines as the basis, um, you really get the benefit of the the um, the generality of the finite element method with the accuracy of the splines. So I would encourage, if you have questions about the accuracy of the method, I would encourage you to review our verification manual.
Great. That last question was from Indrajit, so thanks for that question. Question from Warren. How does the software track convergence?
Yeah, so there's a couple different definitions of convergence. So what I'm guessing that you mean is convergence of the solution as far as an engineer, you care about converging the displacement field or you care about getting a converged stress solution. Um, and so what we do today is that's a manual process, again, using probes to say probe stress at a given location or along a line or to probe a maximum stress value in a region. And then either manually updating your model or again using Python as a wrapper around our tools to then decide itself, like, have I converged? And so if not, then have the Python generate a finer mesh and rerun the simulation. But we don't have any of that kind of functionality internal um, to Coreform Flex. Again, that's on our roadmap as we investigate implementing local refinement. Um, if your question is about convergence of just the actual numerics of the problem, like the convergence of the Newton solver, just done in the traditional manual manner of having residual vectors and um, converging there.
Thanks. Uh, Question from Deanne Song. Is it possible to have a try to use Coreform Flex? I'll go ahead and answer that one. We are welcoming early adopters using Coreform Flex. I think you've seen kind of where we're at from a user interface standpoint and a software maturity standpoint, this is continuing to improve, and we're adding features rapidly. We anyone that's interested, the procedure that we have now is you sit up and have a chat with Greg and myself, and we just determine what application you're interested in. We run one problem for you to just verify that the maturity level and the workflow is suitable for you today. And then assuming that's a check, then we go ahead and give you access to Coreform Flex. So if that's interesting to you, we'd love to have that chat with you. And you can reach out to me directly at matt@coreform.com, or you can go on our website as well to request a trial there. And along with those lines, if you're interested in, actually, Greg, if I could just share for a minute, in a couple of weeks, we have a short course that we're hosting at the IGA conference in Florida. So we still have just a couple of spots left at this short course. If you'd like to come work with us in person, this is 4 hours of detailed instruction working through various problems of the Coreform Flex. It's again co-located with the annual IGA conference. Then just go to our website. There's a link to this from the homepage, and there's just a couple of spots left that you can nab for that. Okay, just a couple of other questions came in. Which contact constraint enforcement method do you use, and have you compared the results with traditional finite elements? From Indrajit.
Yeah. So right now we just use like a penalty enforcement method for contact with like a potential. So, but what I'll say is, again, like any of the methods that you would use in traditional FEA can be used with Coreform IGA. But that's what we kind of currently have. And we're currently working on, additional improvements to our contact approach.
Okay. From Fahim, in those two examples that you showed, you only included elastic properties of material. Can we also include plastic properties like stress strain data? And how accurate is Coreform Flex and failure prediction?
Yeah, so I had another slide that I thought we might touch on, but this is a problem that comes from, there's the Sandia fracture challenge problems that you can find in the open literature. That what I'm showing here is actually our isotropic plasticity J2 model here. So having plastic data, and in this case, the plastic strain, the hardening curve was provided by a piecewise linear function. So yeah, we do support nonlinear materials, not just in the elastic regime, but also in the metal plasticity regimes. I will say that certainly, we don't have a large list of existing material models today in Coreform Flex. Our approach is to work with customers to identify which material models are necessary for them to have success on their problems, and then we implement those materials for them. So if there are material models, again, that you use in your traditional approaches that you'd like to see, you can just reach out to us and talk to us. And what I'll say is that for this example, I didn't include the slide of our reaction forces, but we compared pretty well to the experimental data of this problem. This problem also actually has friction contact between those pins are rigid, and then we have a frictional contact between them and the test plate.
Okay, thanks. A couple questions from Young. What are the primary markets for Coreform Flex? So Coreform Flex is a general finite element solver that we see applications for across many industries. The most interest so far has been coming from automotive and defense companies, but we see applications across a breadth of industries for Coreform Flex. Another question from Young: does Coreform Flex support all element types commonly used in traditional FEA software? And is it capable of analyzing structures that contain a combination of shell, solid, and beam elements?
Yeah, so Coreform Flex today only supports solid elements. The flex representation method that we've implemented or that we've developed does support all of like the different dimensionalities of elements with the same trimming approach. So that is a very general thing that is supported by the underlying technology, but we have not implemented those in Coreform Flex. Additionally, one of the things that we've shown in our verification problems, which again I might encourage you or encourage folks to look at if you're interested, is that we can actually, so like for the Scordelli low roof problem, which is a classical problem in shells, we can actually use solid elements with even less than one element through the thickness. So like with this mesh size, we can solve these problems. And because we use high order elements, we can actually converge to the solution even with less than one element through the thickness. I think the thickness here of this, see, I think if we list it here, yeah, so I think that's a 0.25. And so what you can see is that, like in this case, even with an element size of 2, that's nearly 10 times larger than the thickness of that shell or of the roof. We, this blue curve almost gets the exact solution. And once you even at a mesh size that's 4 times the thickness or twice the thickness, indistinguishable from the solution. So our customers today who deal with thin, like shell-like objects are finding success with this solids approach. We do expect at some point we will need to implement a shell or shell capabilities, but it's not been necessary for our customers today.
Okay. All right. Thank you so much. We appreciate all of the questions. We'll be able to get to most of them. There's a couple of questions that we will go ahead and answer on our form, and we'll also include a transcript of all these Q&A, this entire Q&A session on our website form. So as more questions come in that you think of in the coming days, feel free to interact with us there. And again, we'll be sending out an email with this webinar recording with our contact information. If you'd like to talk with us more about trying out Coreform Flex yourself, then we'd love to engage with you more there. Greg, thank you for your time, and thanks everyone for attending.